Good morning, everybody. Welcome to our webinar presentation today on partial least squares regression. And this is, I believe, our 19th webinar in this series. It's going to be presented by Neal Gallagher and Lyle Lawrence. Neal is Vice President of Eigenvector and has been with the company, well, since the beginning, which I think is about 25 years ago now, and has many years of experience in all parts, aspects of chemometrics. I tend to think of him as our guru on multivariate image analysis. He will start off the presentation, and Lyle will do some of the hands-on midway through the presentation. Lyle has been with the company for 3.5 years and is a software developer, which means a small company means he does everything. So Neal, if you want to go to the next slide. Just some notes before we get started. Please keep your audio muted, not to annoy everybody. We also will turn off video here in a moment, and just to save bandwidth, and recommend you do the same. We will be using, and then if you have questions, please post them in the chat. We'll use the chat feature here extensively. Questions are very welcome, and I will relay them to Neal or to Lyle when you ask them, or they will be answered directly in the chat. We are using PLS Toolbox, our solo version 8.91, though any recent version should work fine. Finally, the WebEx is being recorded and will be available probably in about a day. As I mentioned, we have a long series of webinars now going back for over a year and a half. So they're all quite recent and relevant, and I recommend you take a look at those. So thank you for joining us. I will hand it over to Neal now, and he will get on with the presentation.
Great, thanks, Donald. Really appreciate the intro and you moderating for us today. I wanted to point out that we're going to have several resources available to you, especially these other webinars that have been recorded that you can have access to. And as we move forward, each of these will, be highlighted a little bit, like Lyle's going to be loading data up, etc., and importing data, getting started. But we'll assume that you know just a little bit about PCA, but not a whole bunch, as we show some of the PCA stuff. Donald's also going to throw these links into the chat, so you'll have a place to copy and paste those. But there's also white papers, there's eigen guides, and our wiki is a very important source of information. In the outline, we're going to do a brief discussion of why we do PLS and some of the theory behind it. We're not going to belabor that too much because we want to get right into the hands-on. And Lyle's going to do a example data set called the CGL near-IR.mat, and that is available from our website. It is a data set that you can download. And then I'm going to follow up with some more theoretical type concepts in a data set example using an octane rating that is available in Sol from the demos folder. So why regression? What do we do with regression? Well, the idea is that we often have something that might be expensive and hard to get, and that's really what we're after. And we can find something that we can measure that's close, but it's not exactly the same thing. And so we want to develop a mapping between an X block and a Y block. And that mapping is our regression model. So the regression analysis is going to create a mapping between these two blocks. And in both examples, we're going to use an X block that is a spectroscopic measurement. And the Y block, we're going to be looking at a protein concentration for the first example and an octane rating in the second example. So partial least squares is really one of the most popular linear methods for regression. And in chemometrics, I think a lot of people assume that if you're doing chemometrics, you're doing PLS. But it's just one of the methods. It just happens to be very popular and very useful. We often use PLS models to obtain estimates, i.e. predictions for a Y block of data from an X block of data. But we also use regression analysis for exploratory analysis to try to understand our system that we're measuring and working with. So we're going to use PLS for quantification today, but it can also be used for classification and detection. And the model, and this is going to be one of the very few equations that we show, is an inverse least squares model that assumes that we have our measured X block, and we're going to try to create a mapping to our measured Y block, or our reference values. And the mapping is this regression vector. So it's a linear model. X times B is equal to Y. And the PLS model, all of these models, I try to identify what this mapping is. All that is it's identifying what this regression vector is. So that's what PLS is doing, is identifying that particular vector of coefficients. Well, okay, I am going to show another equation, but this is not to do linear algebra. It's just to show you that there is a loss function that is a sum of squares, and that loss function is being minimized. And the most intuitive way to minimize that is in a least squares sense. And it leads to an estimate of this regression vector that looks like this. Okay, we don't have to worry about what all this linear algebra is. We just need to see that there is an inverse here. And what that is it's sort of like a matrix division. And in MLR, multiple linear regression, we need to take an inverse of X transpose X. And the problem with MLR is that sometimes this matrix division doesn't exist or is really difficult to calculate because the inverse is almost not existing. In other words, we have an ill-conditioned problem. So partial least squares is really one approach that attempts to deal with this problem where we can't get this matrix division, because we don't want to divide by zero, essentially. Well, in principal components analysis, that's another way that we would attack that problem, getting rid of that ill conditioning in the data set. And the whole idea, remember, from PCA is that you have your X block and you decompose it into scores and loadings. Excuse me. We build our model, our PCA model, intentionally so that this portion of the decomposition is full rank and it is invertible, so we can solve the problem. The deal with principal components analysis, however, is that the P, this basis set of vectors that describe the variation in X, were really selected in a way that maximizes the capture sum of squares in X without consideration for the regression objective, i.e. our identification of the regression vector. Now, partial least squares has a very similar model to PCA. It breaks it into this full rank portion that we can use to build our model on, and a set of residuals that we don't get any inverse of, we don't have an interest in. However, the scores, the T, and the loadings, P, the basis that we're working with, are really found differently for K latent variables. So we're no longer calling them principal components. We found them differently. We've rotated away from the PCA solution to a PLS solution. And again, don't need to really look at how all this linear algebra works. We just need to see that the P in PLS are going to be found by maximizing the covariance between our X block and our Y block. And that's a different objective than what we used for PCA. So another way to look at that is graphically. You can imagine, if you will, that I have an X block that just has two variables, X1 and X2. And if I do principal components analysis, I get my first principal component lies off in this direction here. My second one is orthogonal to it. It points off in this direction here. And my ellipse of constant hoteling t squared is drawn around the data like this. Well, if I do MLR, if I'm capable of getting an inverse, that thing that we do a matrix division, if that works, this is the direction of the MLR vector. And what it's doing is it's trying to capture the most correlation between the X block and the Y block that we can possibly obtain. Now, the color by here is I'm coloring by the Y value, and you can see that it really is parallel to this direction here. Well, in PCR, if I built a model on a basis that had only one factor, it of course is going to fall in the direction of the first principal component. Well, PLS is trying to capture something that's in between. It's capturing covariance between Y and X, and the PLS vector, regression vector, lies between the PCR, first principal component, and the MLR solution. So that's what PLS is trying to do, is capture covariance in the basis of describing X. And then we can switch over to Lyle, and he's going to show you a hands-on example.
Great. Thanks, Neal.
Oh, you got to grab it from me.
I got it.
Yeah, okay.
You see my screen okay?
Oops.
Looks good. Did for a moment.
Yeah. My bad. Sorry about that, Lyle.
Oh, you're fine.
Yeah, we can see it now.
Very cool. So now that we have some background and some theory on PLS, let's jump into the software and do an example and get our hands dirty, so to speak. And so we're going to be using that data set that Neal mentioned earlier, and this data set has 231 samples in its original form, and it's a 3-component mixture design data set. So it's a design of experiments. It's very clean data, so it'll be easy to work with, but just note that it's very clean and it might not represent real world data. So Neal mentioned X and Y blocks, and so in this case, our X block is going to be NIR spectra of 117 wavelengths, and our Y block is going to be our components that were mixed together to generate these NIR spectra. These consist of casein, glucose, and lactate, and there's a moisture variable in there as well, but we won't be using that. And these are all in units of weight percent. So I'm going to switch out of PowerPoint now. I'm gonna bring up Solo. So I already have Solo opened. So when you launch Solo, this is the window that you first get. If you're using PLS Toolbox, you can get this window by typing browse at the MATLAB command line. And if you're interested for that information, I recommend watching our Getting Started webinar, where it goes through this information, and it goes through this window, this workspace browser window, and gives, goes into detail about that. So I want to load my data. So I have here the mat file with my data in it, and I just found it on my system here, and I can just click on it, drag it, and drop it into my Solo workspace here. So now we see we have our 6 variables here, 6 data set objects. The first 2 are the original data set objects with our, this first one is going to be our Y block, has our properties that we're interested in. Second one's going to be our NIR spectra. And then the other 4, we've actually already split this data into calibration and validation data. So it's about 2/3 split. So 2/3 are kept in the calibration, and then 1/3 is in the test set. So now that we have this data loaded, I actually want to bring it into our PLS analysis window. So here on the left, we see in our analysis tools pane, we see under my favorites, we have PLS entry here. If it's not there for you and under your favorites, you can find it under the regression section. So here, if I expand this regression section, towards the bottom, I see PLS, and it's among all of our other regression methods here. So I'm going to collapse this regression section. I'm going to launch the PLS analysis window simply by double-clicking on that PLS entry. And this will bring up our PLS analysis window. And again, for more information about this window and the details of it, I recommend our Getting Started webinar. So now to load our data into this analysis window, I'm going to right click on this X block here. So this is our calibration X block. It's currently empty. I'm going to right click on it. I'm going to say load X and Y. And it's going to prompt me to select data to load. It's going to say select X block data. And it's looking in my workspace for what to load. And so I'm going to select XCal here. So this is our X calibration. This is our NIR data. I'm going to say load. And then automatically I'm prompted to load my Y block. And I'm going to select YCal. So now that we have our data loaded, we can confirm it's loaded simply by hovering over our X and Y blocks. So here's our X block. We see that it has size 153 by 117. So we have 153 samples and 117 variables here, in this case, wavelengths. Similarly, for our Y block, we have 153 samples. And we have 4 variables, and then you can see there's a little bit of a caveat here where our included field, we actually have 3 included. So we have 1 variable that's been excluded. That's that moisture variable, and we're not going to worry about that. But the data is there for you to play with if you go get this data from our website. So next thing we do, and highly recommend doing this, is to plot your data. So before building your model, we recommend plotting data. I'm actually going to clean this up. I'm going to minimize that window real quick. So to plot the data, I'm going to right click on this X block and say plot data. And now what we see, this figure comes up, and we also see our plot controls window come up. So all of the figures in Solo or PLS Toolbox are going to be controlled by this plot controls window. And you could have many figures open, but you only ever have one plot controls window. So right now I should have one figure open and one plot controls. So I have here the mean spectrum plotted of my NIR data. If I want to plot all of my data, I can simply click on the data here on this Y. So choose data for Y axis, and I want to choose data, and it's going to plot all my data. So this is all my NIR spectra. And again, this NIR spectra is mixtures of the 3 components, casein, glucose, and lactate. And we can see it's very clean data. The absorbances aren't too high, so it's going to be easy to work with. And that was kind of the point of this data. And then the next thing I want to show is, I think, a pretty powerful tool for exploring your data, especially when doing regression. And it's our color by tool. So down here in plot controls towards the bottom, we have this color by button. And you can click on it, and it's going to ask you, what do you want to color this data by? And it knows that we have data in our Y block. So we have a Y block loaded. So it's asking me if I want to, so I can choose to load from my Y block, which I will do. So I'm going to say load from Y block. And then it's going to ask me, okay, what column or what variable in my Y block do I want to color this data by? So you can choose from any of them. I'm going to select glucose here and say, okay. And then we see that our lines here change to these colors, and I'm going to put a color bar on this plot. So if I say insert color bar, it's going to give us a little bit of context of what the colors mean. And so with the color bar, we can see here, red, it's going to mean for higher values of glucose, and these numbers here on the color bar are in units of weight percent, which are the units in our Y block. And so we see a nice trend between high glucose values and high absorbance values. And similarly for low absorbance values, we have low glucose. And so this is a great plot to explore your data, and it's very useful. And if I were to see this on my real world data, I would be hopeful that a regression model will be successful. And I'm going to close out of here. And so we have, if I hover over my Y block, we see that we have 3 variables included. So I actually don't want to build a PLS model on all 3 variables. I will say that PLS Toolbox and Solo can do that. It is possible, but I don't want to do that for this example. So I'm going to right click on my Y block and say select Y columns, and I just want to include my glucose column here. So I'm going to select glucose and say OK. And then we can confirm by just hovering over, and we see that, okay, we only have 1 column included, 1 variable included. So that's great. So the next step to think about when building a PLS model is the pre-processing to use. And we have a webinar coming up about pre-processing, so I recommend you check that out for more information about pre-processings. But for now, we're just going to leave pre-processing in our Y block to autoscale. Autoscale on data set with one column is the same as mean centering, so that's why I'm just going to leave it as autoscale. If I hover over my X preprocessing, this P here, I see that it's also autoscale, and normally we don't autoscale spectra, so I want to change this. So I'm going to click on this P and say edit preprocessing. So this is going to bring up my preprocessing window, and you can see here on the left are available methods. So there's quite a lot of them. So preprocessing is quite a heavy topic to cover, which we won't do today. And then on my right here, we see the selected methods. So this is the methods that are going to be applied if I go forth with this, but I don't want to use autoscale. So I want to make sure autoscale is selected in my selected methods here. I'm going to say remove. It's going to take it out. So now there's none. And I'm going to find mean center in my available methods. It's down here in the scaling and centering section. I'm going to select mean center and say add. Okay, great. So now I've changed from autoscale to mean center, and I'm going to say okay. Hover over that just to confirm that it's working. Another thing to think about, and this is important, and we'll show a few slides about this, is cross-validation. So we can open this cross-validation window, and we're going to leave it as it is right now, the defaults, just Venetian blinds and the number of splits, and then we'll look in a little bit about why or how cross-validation works and why it's important. So I'm going to close that, and so now we're ready to build our first model. And to do this, we can simply click on this model block. It's going to think for a second, and it's going to build our model. So now we built our first PLS model, and we see this variance captured table here. So what this is showing us here, we have these rows. So these rows correspond to our latent variables, and then the values in the table correspond to the percent variance captured in our X block and percent variance captured in our Y block. And then we also have here our root mean square error cross validation for the analyte that we're interested in. In this case, it's glucose. And so we can get a plot of this information. If we go up to our toolbar and we find the lambda symbol, the button with the lambda symbol, we can, and if you hover over it, it says plot variance captured and cross validation results. So we can click on this. And we get this plot. So it's useful here since we have two lines to put a legend on. So I will put a legend on. It's right here. The button for the legend is right here. Insert legend. And we see here we have this green line, which is our root mean square error calibration for our glucose. And then our blue line is our root mean square error cross validation. So this plot is useful for helping us determine how many latent variables to keep in our model. And with that introduction, I'm going to switch back to PowerPoint. I'm going to go to the next slide. Sorry, my toolbar won't go away. All right, one second. Okay, so here's a screenshot I took of an analysis window where I built the model, and you can see here that I've selected the third latent variable, and it says current, so this is a current number selected latent variables. And above that text, there's a word that says suggested. So suggested number latent variables. So the software is recommending how many latent variables to keep. And so we often get asked how it's doing this, how it's making this recommendation. And what it's doing is it's looking at cross-validation. And so the idea behind cross-validation is we're going to divide our data set. So in this case, our NIR data and our Y block data into sample subsets, and we'll call them J. So we have J subsets of our samples. And then for each of these subsets, we're going to take that subset out. So we're going to take those samples out of our data. We're going to build a regression model using the samples that were left in. So the samples in the remaining subset. We're going to apply the model that we built to the subset we took out, to the samples we took out, and then we're going to calculate this predictive residual error sum of squares for the subset that we took out. So it looks like this, the equation. So the error is the y measured minus, this will be your y predicted here. And then we're going to do that for each subset, and we get our root mean square error cross-validation after we sum up the error for each subset, divide by the number of samples, and then take the square root. So that's how we get that root mean square error cross-validation. And it's very useful for helping us determine the number of latent variables in that plot, and we'll go back to that plot in a little bit and kind of look at it some more. But we look for a minimum or a knee in that plot, that root mean square error cross-validation plot. So that helps us choose what number of latent variables to keep. So I'm going to go to the next slide, and this is this is cross-validation but graphically. And so simply we have our data set here, and we have our subsets represented by the different colors. And we're going to do 3 rounds, so we have 3 subsets. So we're going to do 3 rounds where we take one subset out, build a model with the remaining subsets, and then use the subset we took out to predict. And then for each of those subsets, we're going to calculate the prediction error. So it is important how you form your test sets or your subsets. And so here is a look quickly at some of the options in the software. So the default is going to be Venetian blinds. It seems to work on most data if it's in a random order. Contiguous block works best for time series. Leave one out. It works well for small data sets. It can take a while if you have large data sets and be overly optimistic. And then there's also custom. If you know certain information about your data and you want that to be captured in the cross-validation, you can do custom. And as well, just like pre-processing, cross-validation is a heavy topic and a lot of things to talk about and to discuss, which we've done in a webinar. So you can, go view that webinar, and Barry, the president of Eigenvector, he spends an hour talking about cross-validation. He shows you in the software how to do custom selection and things like that. But just know that how you form those subgroups will affect your root mean square error cross-validation, and thus could affect how many latent variables you select, and this could lead to over-optimistic results in your PLS modeling. So now I want to introduce these terms a little bit more. So we've seen the root mean square error of cross-validation, and we saw on that plot the root mean square error calibration. So these root mean square error terms, so these are used to assess a model's fit to the data, and they're also used to assess the model's predictive ability on new data. And so these are the measure of average deviation of the model estimates from the measured data. And this first one we're seeing here is the root mean square error of calibration, and this is a measure of the fit. And here's the equation where we just have our measured y minus our predicted y. For all the samples that are used to build the model, and we sum that up, and we divide it by the number of samples and take the square root. But the important point to note here is that the root mean square over calibration is a measure of our fit. So fit, calibration, root mean square over calibration is a measure of fit. Going on to the next slide, so our root mean square over cross-validation. So we've seen this before, and as well as helping us determine the number of factors or latent variables to keep, it's also an estimate of the predictive power of our model on new data. So it looks like this, and we saw this in a different form on the other slide, but we're gonna split our data into the subsets. You capture this error term for each sample in the subset, do that for all the subsets, and then average that, and we get our root mean square error cross-validation. So M here is the samples not used to build the model. So this sample is taken out of the model. And then the last term, and this is very important here, is our prediction error. So we haven't seen this term yet, and we'll see it in a little bit, but this is the a very important value. I think I will say sometimes in the literature it's underreported. So I think when you're looking through the literature and looking at PLS or papers talking about PLS, I would look for make sure they do a root mean square error prediction. I think that a lot of folks stop at cross-validation, but the prediction error is often used to validate a model, and it's the true measure of the predictive power on new data. While the root mean square error cross-validation gave us an estimate, the root mean square error of prediction gives us, a better measurement of how well this model will predict on new data. And so measure of the prediction error, root mean square error of prediction. Here's the equation. Looks very similar. In this case, M here, it refers to the samples not used to build the model. Okay, so I'm gonna switch out of PowerPoint and go back to Solo here. So now here we are. We're armed with more knowledge about root mean square error, cross-validation, and calibration. And so knowing that, root mean square error cross-validation can help us determine the number of latent variables to keep in our model. Looking at this plot, I think we can, choose from a few different ones, but I think latent variable number 8 sticks out here in that we have a large drop in root mean square error cross-validation from 7 to 8, and then there's not much of a drop 8 and after 8. So I would say it's comfortable to start here with latent variable number 8. So I'm going to close this window, and you see here our model is currently built with, or is keeping 5 latent variables. So to change this, I can simply double click on the row here, on the 8th row. So it's going to set it to the current. So now we're keeping 8 latent variables. So you see that the software suggested 5. But we're not going to take what the software suggested, and we're going to do 8. So, another point is you don't have to take what the software tells you. Use your eyes and plot the data, and use what you know about the data, and choose what works best for your data. Okay, so now we have our model built. We have our number of latent variables that we want to keep. And so the next step would be let's take a look at this data a little bit closer. And sorry, I went too fast. I'm gonna close that. Let's take a look at this data a little closer. So I'm gonna click on the Erlenmeyer class. So this is our plot scores and sample statistics button. So this is gonna bring up a figure, and this figure has multiple plots on it. So I'm gonna make this window a bit bigger here so we can really explore this. And I wanna go through all of these plots, some in more detail than others. So this first plot here is our Q residuals, our reduced Q residuals versus our Hotelling T-squared plot. And for any of these plots, if you double click in the white space, it's going to bring this plot out into its own figure. So now we have this plot in its own figure, and we can see everything more clearly. So this plot is useful for determining outliers here. And in the PCA webinar, we go over Q residuals and T-squares quite a bit. So I recommend checking that webinar out. But the hope here is that using this plot to pick out outliers for exploring to see if they should be excluded from the model. So I'm looking for points here with high Q residuals and or high T-squares. So I see this point here at the very top is a candidate for of being an outlier. So I want to explore that a little bit more. And so it's going to be useful to know what that sample is. And we can do that easily by making a selection here. So we have a selection button here. If you hover over it, it says make selection. So I'm going to click on it. We get some instructions on how to select, but your cursor will turn into these crosshairs. You can simply drag a box over the sample you want to select, and now you see it's turned to this magenta or purplish color. And if I move this window out of the way, you'll also see in those other figures that it's highlighted that sample in those other figures. So now we can see, okay, this sample has a high Q, so where does it lie in all these other plots? So we can see that. So that's a nice feature that's really useful for exploring outliers. So now that I have this figure or this sample selected, we can find out the sample number that it is. And we can do that by saying view numbers on and off. So this button here with the 1, 2, 3, we can click that. And so that's gonna put a number on this one selected sample. And we see that sample 44. So now we can say, okay, now I can go back to my lab notebook and say, okay, did something happen weird with sample 44? And is it a true outlier? Or and it can be excluded from the model, so on and so forth. So great. So we've looked at that. And so there's another sample down here where that has a high t-squared. So we can actually highlight that sample as well. So I'm going to make another selection. So I'm going to click on Make Selection. So I want to add that to our current selection. So I'm going to hold down Shift here. So our instructions say hold down Shift to add. So I'm hold down Shift and then draw a box. So we have sample 70. So since I have numbers turned on, it automatically put the numbers on that sample as well. So 44 and 70 are potential outliers that we want to go investigate. So I'm going to leave this figure up for a little bit. And I'm going to go on to our next plot here. So I'm going to double click on this Y studentized residual and leverage plot. So this plot is useful. So the Y studentized residuals is it's a deviation of Y values from the model. So this helps us determine if we may have some Y block outliers. And the scale here from on this Y-axis, on this Y studentized residuals, can be thought of as standard deviation. And these blue lines at 3 and -3 can be thought of as 3 standard deviation and -3 standard deviation. So we don't expect too many samples to be outside of these lines. And if they are, they are potential outliers. And leverage here, so leverage is a measure of how influential a sample is on the model. And we certainly don't want outliers influencing our model too much. So one of those samples that we selected, I believe this is 77 here, or 70, that had a high t-squared, also has a high leverage. So that's a strong candidate for being excluded as an outlier. So I'm going to speed up a little bit here. So we have scores down here. So this is scores. So scores plot is how samples relate to each other. And this highlights the 3-component mixture design of this data. So it's very clear it makes a triangle. Then it just highlights how clean this data is. You can also determine outliers in real world data. You might have a sample out by itself on the scores plot. So that would mean it's not like any other of the samples in your data set. So that should be certainly explored. And then our next plot, which is probably the most sought after plot, is going to be our Y cross predicted versus our Y measured here. So this plot is, I think, what most people jump to before looking at the other ones, because it can give you an idea of how well you're doing, how well the model is predicting. And so I'm going to insert a legend here. So we see here, it's kind of hard to see because this model builds so well. We do have a red line and a green line. The red line is the fit of the data, so it's the univariate fit to the prediction of the data, and the green line is going to be our one-to-one fit, so that's if it predicted perfectly. And yeah, for now I'm gonna leave this as is. I'm not gonna go too much into this plot at the moment. So okay, so we've selected. So I'm gonna go back to this plot, so my Q and T squared plot. So we've selected some potential outliers. So now I want to exclude them. So I've done my due diligence and I've determined that these are true outliers and I want to exclude them. So this can be easily done with the point selected. I want to go to Edit in my plot controls window. So here in plot controls, Edit, I'm going to exclude selection. So what this is going to do is going to exclude these samples from the data set. And so I turned on all my numbers here, which I don't want because that's cluttery looking. I'm gonna turn those off. I'm gonna go back to my analysis window and then hover over my X block. Okay, we see that we've excluded 2 of our samples. So our first dimension here changed from 153 to 151. And so those samples aren't deleted, they're still there, they're just excluded. So they won't be taken into account during the model building process. So I'm gonna build this model again, and just simply by clicking on model. So it built the model and it actually updated all my plots for me. And now we can explore again the same, what we did just now, we can explore now and with this new model built and see how we performed. Okay. So I want to show you real quick how to apply this model that we built to new data. So I'm going to close all my windows here. So here in our validation X and Y block, I want to load the test data that I have. So I'm going to right click on my X validation block and say load X and Y. So it's going to prompt me to select the validation X block. So I'm going to select X test. It's going to prompt me to select the validation Y block. I'm going to select Y test. And now we have an exclamation point here. So it's saying that we need to do something. And in this case, we need to click here to apply the model to this new data. So we've applied the model, and now we want to review the results. So we click on our Erlenmeyer flask, and we get those same plots open. So you want to explore those plots again to see if you have any potential outliers. So in this case, we're plotting the validation data, so the test data, so we're showing the 78 test samples here. So I'm going to go straight to this Y predicted and Y measured plot. I'm going to double click on the white space to bring it into its own figure. So remember, this is just the 78 validation samples. I'm going to turn on a legend here so we can get a better idea. And then what you can do is you can right click on this plot in the white space, and then you get these values that we were talking about, the root mean square error calibration, cross validation, and prediction. And we can select show on figure to put these on the figure here. And you can take a screenshot, and this would be a nice way to pass around results to your colleagues and things like that. Another point I want to make is that if we want to show the calibration data with this test data on this plot, in the plot controls window towards the bottom, there's a show cal data with test button. So we can click that, and it's going to update our plots to now have our calibration data. So it's going to go through, update our plots, and we see that we have our calibration data is in the black circles or the dark gray circles, and the test is in the red diamonds here. Okay, great. So now we have all of our values. We see that root mean square error prediction is a bit higher than our root mean square error of calibration and cross validation, which is to be expected. Okay, so I'm gonna close that. So the last thing I want to show really quickly, I'm digging into Neal's time here, is we often get asked where to find the regression vector for a PLS model. So I clicked on the loadings plot button, which looks like a spectrum here, and that brought up another figure with plot controls, and we can find the regression vector down in this plot controls window here. So here's the regression vector for my PLS model. And we show in the Getting Started webinar how to kind of export from a figure to CSV or Excel files. So that's another question we get often. Okay, I think that's all I wanted to show for now.
And those regression vectors are kind of hard to interpret. We typically caution against that.
Yeah.
Unless you have a really simple system, they're going to be tough to interpret real well, because what it is it's something that's parallel to your Y while being orthogonal to all the other variation in X. And you go, well, all that other variation can get quite complicated. And the orthogonality part of that also makes it tough.
Yeah. Thanks, Neal.
You ready to hand it back?
Yes, sir.
All right.
Stop sharing.
So I'm going to use another short demo here, and this is coming directly from our demos folder in Solo. So I'm going to switch over to Solo, where I've already loaded things up. I'm going to grab the spectra, which are near IR spectra of gasoline samples, and I'm going to drop it on to my partial least squares in my favorites over here, start up an analysis. And I'm going to try to predict octane from the near IR spectra of the gasoline. So this will be my octane, is now my calibration Y. We load that up. And my pre-processing for Y, I could leave as auto scale, but I'm going to use mean centering here for this example. And my pre-processing for the near infrared spectra, I'm going to edit my pre-processing here for X. I like mean centering, but I'm also going to add a little bit of Savitsky-Golay derivative in here. And near-infrared spectra often have offsets and slopes, and derivatives are very useful for accounting for that kind of thing, but it can make your pre-processed spectra look funny. I have a settings button here, and in the settings, I'm going to change my filter width because this is a window-based technique, and the pre-processing webinar will talk about this quite a bit more, and we also have a white paper on it. And in this pre-processing, we have a window of 11, which means that on the ends of the spectrum, where I don't have a full 11 channel window, I'm going to have some weird stuff going on. So I'm going to trim off in this data set the last 5 points on either side because those can be affected by end effects. However, they're going to be used, if I have this checked, to calculate the filter. So I like to keep that checked. So I've got my pre-processing set. I'll say OK. I can plot my data. And we typically plot our data. The summary plot comes up. I want to plot all of my data on there. So I click on all of the data. And I say, well, this is interesting. I've got some weird thing going on over here. And I don't know what that is. So let's continue on with the exploratory analysis. I can just build a PLS model in exploratory fashion. So it's building a model very quickly. Uh-oh. There we go. I thought it was going to go a lot more quickly. And it's got no cross-validation used. I can look at my scores. And one of the things that comes up is, oh, I see some patterns in here. And my data set has been annotated with classes. And if the class name is available, I can see that I have gasoline present. And this bottom one winds up being gasoline with alcohol in it. Ah, okay. So we're trying to predict octane for both of these groups. And it looks like on the left-hand side with our predicted, we're doing a reasonably okay job with our 4 latent variable model. If I come back to this plot of the data, I can also click on my show classes, view the classes that's available, and I look at my data, put on a legend, and I can see clearly that the weird ones out here are the ones with alcohol. Ah, that's great. That's okay, because what PLS is trying to do is provide enough latent variables that it accounts for variation in my data and allowing me to create a linear model for octane. But in this example, what I want to do is I want to select this class. So I'm going to right-click my alcohol data set, say select class, and I'm going to exclude it. I'm going to build a model that doesn't have the alcohol data in it. So I'm going to exclude that selection. And it's been excluded. I'll close my plot over here. And now I'm going to add my cross-validation. So I click on this check mark over here to get my cross-validation up. I presently have none. And I may use with 33 samples of Venetian blinds with a small number of splits, but just for this example, I'm going to try to leave one out. As Lyle mentioned, this is often an optimistic guess if you use leave one out. So we typically try to leave out larger numbers of samples in our cross-validation. Webinar on that's pretty good. So I'll apply that and close it. We'll calculate a model on just the gasoline samples. And we'll look at our cross-validation curve by clicking on the eigenvalue plot. And here now I have my RMSE-CV and my RMSE-C. And this, I think, is probably a more typical RMSE-C kind of a plot than the really beautiful one that Lyle had. But what you'll see is I've chosen 4 latent variables, which is down about here. And the RMSE-CV is a little bit bigger than the RMSE-C. RMSE-C continues down. And in this plot, what I really want to look at is not the predicted, but the cross-validated predicted. There it is. And the cross-validated predicted down here is a better look at how your predictive capability is going to work. I can select my outliers in the queue. And why I say it's predictive is because it's the ones that are being left out of the modeling step. And the whole idea behind cross-validation is to try to find a basis in the X block that's predictive for future samples, not just for fitting. So I've got a couple of potential outliers, and I'm highlighting them here. I've also got one potential Y block outlier down here. Now, in validation, when I'm doing predictions, I often, in my online environment, don't have validation reference values, so I wouldn't be able to see this. But in my calibration, I can look at this guy and say, aha, there's a sample there with the numbers on it. It is sample number 32, has a little bit bigger number. For comparison, I'm going to go to the right-hand side here, and I'm going to plot measured on the x-axis, and then my fit values listed as Y predicted. And it looks like I've got about the same spread around this green line, the 1, 1 line. So that spread, the standard deviation around that line, is my RMSEC on the right-hand side, RMSECV on the left-hand side. Well, what would happen if I clicked on a model that had 8 latent variables? If I click 8 latent variables, you'll notice that my plots are going to update and my Q outliers are now inside my model because they're now being captured by a couple of latent variables. However, they still have a high t-squared and a high leverage. And leverage and t-squared are very closely related. So it makes sense that these two are both out. You'll notice that it looks like we've done a little bit better on number 32. However, in cross-validation, it's about the same. It didn't really change that much. But in fit, it did change. So we're starting to capture a little bit of nuances, maybe even noise in our data to try to explain that kind of thing. Now, one of the tendencies that we have is to go into our model and say, well, look at this, RMSEC is going way down to out here. Why don't we keep a lot of factors? So I'm going to do that. I'll show you what happens. I'm going to click on 26 factors, double click this and build my model on 26 latent variables. And as I keep more and more latent variables, I get closer and closer to the MLR solution. Well, notice what happens to my RMSEC. Well, of course, the left-hand plot is telling us exactly that this is going to look fantastic, and it does. Over here on the left-hand side, I'm doing cross-validation predictions, and if I leave just one point out, look at this guy. He's poking way out there. We didn't capture him. So he is clearly an outlier in this case. But I've built 33 different models over here, and in each case, I've grabbed a different basis, bunch of vectors in latent variables in the X block to try to describe the Y block. And when I make predictions, I'm getting fairly poor predictions compared to my 4 latent variable model. So this difference here is showing you an indication that we're overfitting. We're trying to fit too hard. So let's go back. Let's build a 4 latent variable model. Very easy to do. So now we're back to a 4 latent variable model. And the next question I've got is, what happens if we try to make a prediction for the data we left out, the alcohol data? Well, if I click this button, it says view excluded. So it's almost like doing a test, just the way that Lyle loaded up his test data into the validation blocks here. But you'll see, here's my gasoline with alcohol samples. They have really high Q residuals. That's an indication that the model, the PLS model, is not capturing the variance that's in this data. And that makes sense from our plots that we made. And it also is showing very bad predictions for these alcohol samples. And that makes sense. We didn't model them. One of the biggest things about this is that if you have future samples where you have high Q residuals, you don't trust the predictions. You don't trust the predictions for high Q residuals. That sounds like a bad thing. why is PLS making these bad predictions? The truth is that PLS is doing a fantastic job because it is giving you a red flag that these data points don't look like the data that you built your model on. So you can't trust the predictions for these guys. And so that's a tip of remember to look at your Q residuals. Okay, with that, I'll run back to our presentation and we'll bring up some summaries. Remember that PLS is a linear model. We've got an X block we're going to predict from to make predictions for a Y block, and our whole process here in PLS is to identify this regression vector B. The other part is that we're using cross-validation to estimate the number of factors or number of latent variables that we're going to use in our model, and we try not to overfit. Fit and prediction are two very different measures of a model's performance. Our prediction is really a measure of the reproducibility of our model. So what we're going to do in cross-validation is try to mimic prediction, and it says that we're going to estimate a new subspace in X for every CV cross-validation subset left out. And therefore, that subspace, those latent variables that are capturing variability in X, they're going to flop around a little bit as we do cross-validation. But we're trying to find the parts of that X that are most predictive for Y. And there are prediction statistics. So when we do predictions, we always get our X block statistics, Q, lack of fit, and our T squared, which is our in-model distance from the centroid. However, we don't typically get these numbers for the Y block during prediction, like in an online environment. So the Y block measurements are necessary from time to time so that we can get be able to check our model, see if it needs to be updated. Remember that high Q predictions should not be trusted. We get interferences that can bias our predictions in unknown ways. However, with these linear methods, we've got more forensics available to us to look at why it's out. And in the end, this last part, we talk about our RMSC for calibration, fit, cross-validation, estimated prediction, and our test set prediction. We love it because it's in the units of Y variable. Correlation is necessary but not sufficient for describing how good a model works. And so we often say, okay, that's great. We've got an R squared. Some people really like to look at those. But these RMSC numbers are the ones that are most important. And lastly, as I exit this, I want to say once I've got my model built, I can actually export this thing to a file, to a predictor, or a regression vector given some of the pre-processings, etc. So these tools allow us to go into a different environment and make predictions with our PLS model. Okay, Donald, with that, I'd like to bring the presentation part to a close, and we've got maybe some questions.
Thanks, Neal. That was a nice presentation. Yes, we do actually have some questions, and kind of mostly a lot of them are relating to the pre-processing. For example, there was a question about do you need to mean center your Y block in PLS? And
right. Well, the answer there is that if I mean center my X, I'm also going to mean center my Y. If I don't mean center both of them together, that's a force fit through 0. But if I mean center both of them, it allows for an offset. So if I looked at that equation in this, oops, where am I here? Up. It'd be sort of like adding an offset term in here if I mean center both of them.
And it's usually recommended, and you can certainly test by not doing it. And I think you'll usually find that you get a much worse prediction, cross-validation or test prediction. Oh, and one other comment just that comes into help desk quite a bit is that you only need to specify the pre-processing on your X and Y once, and you do that as Neal and Lyle showed. You don't need to like re-specify it for applying for the test data, for applying it to the test data. The pre-processing is contained in the model. That question actually probably comes up a little bit more often when people are working at the command line. And also all of this is also you can do at the command line, and you can look at our plsdemo.m if you're using MATLAB PLS Toolbox. So there's actually quite a few questions came towards the end. Let's see. So here's a question. How can you predict for sample concentrations of future samples when you have to fill in X and Y blocks to predict? Is it possible to not fill in the Y block? So for the
it is possible. You don't have to have the Y block. If you just load in the X block into your test set here, you'll make your predictions. Just like we had out here. The thing is that if you have a Y block, you can then test your predictions. And that's actually what we refer to as validation step.
Great.
And, you know, if you're doing an online environment, you're essentially doing just the X block, right? So.
Right. Let's see. For PLS DA, variance in Y block captured by model can be quite low. So we're not really talking about PLS DA classification here. I don't really want to take a stab at that.
We're not. We do have a nice webinar on it, though. On DA, and you don't cross-validate on variance captured on Y. That's not our interest. It's on the classification part, so it's different.
Here's I think a very relevant question. What is an indication that you are overfitting your model?
Well, this plot is one of our best indicators. You know, this is the cross-validated. That's your prediction, and there's your calibration. And so if this cross-validation number starts getting big compared to our fit number, then we're getting close to overfitting. And there's going to be, there is a nice webinar on the cross-validation stuff that I would highly recommend, but this is one of your best ones. I recently saw an example where somebody showed this beautiful fit and then leave one out over here was just really bad, like I showed with the 26 latent variable problem. And that's another indication, but it's essentially redundant information with this plot over here.
Yeah, so RMSECV is a good guide there, but it's also a good cautionary note that it's really good to keep a separate test set and as a validation set, because sometimes the cross-validation may be a little bit optimistic and deceiving you. So it's possible to keep a separate test set.
And you want your test set to be statistically independent as best you can from your calibration set.
Neal, can you bring up a loadings plot and show a variable importance and then also a regression vector? Those two questions came up.
Okay. I'm going to click over here on the right-hand side, and I'm going to put, I'm going to hit it number 3. What that does is it's a little short circuit, gets me to a...
Neal, can you just go back and show which icon you clicked on from the analysis window?
Here. Plot loads and variable statistics.
Thanks.
You bet. And so the top one, I'll plot the regression vector. I'll click on this one, and I'll plot the VIP scores. And down here, I'll plot the selectivity ratio. And this is one way to do a variable selection, and this is another one. And it's interesting often to do them together to say, aha, these look like they're the most important variables here. Maybe these guys over our limit line. But it's a little different from what this approach uses. And so understanding a little bit of how the variable selection is working is sometimes tough, but it'll help you interpret these plots better. And we also have a webinar on variable selection.
Thanks, Neal. Here's a simple question that's always good for discussion. Are samples with t-squared greater than 1 always considered outliers?
Not always, no. And in fact, an interesting thing is if you look at the plots that Lyle was making with that design of experiments, the points at the corners of that ternary diagram probably have a relatively high t-squared because they're so far away from the center, and yet they're going to be some of the best data points for helping us identify that regression vector. So in DOE, high t-squared's not, but in something like this, it's maybe not designed as well. And if I hide those, turn off my, oops, I hit it twice. Let go. Somebody like this, he's not above 1. You can go out a little ways. I mean, statistically, you're going to have something is always going to poke out a little bit, but. And this is the 95% confidence limit line. So our reduced statistics are ratioed of the t-squared statistic to the t-squared at the 95% here. And we can change that number as well.
Right, that's an important point, is that it's if you're talking about an absolute value of 1, then you probably want to be talking about the reduced t-squared, which is the ratio relative to the value at that confidence limit.
And I can plot just a regular t-squared. Oops, that's my y. Regular q.
There was one question which I didn't really know the answer to, but somebody proposed an answer, and that was, why is it called partial least squares?
Oh, because it's not fitting the whole X block. It's taking latent variables and identifying a smaller portion of it. So they were saying partial, and that was a little, I think, confusing at some point. And another acronym came out. And they said, well, it's actually projection onto latent variables or latent structures.
Yeah, and thanks, Mohammed, for your comment on and answering that too in the chat.
Neal had a question. Is it better to look at loadings or weights?
I like to look at both. Weights, I like to look at weights myself more than I like looking at the loadings. But oftentimes, let's put a loading up here for number 1, and let's put a weight here for number 1. And you'll see that oftentimes they're not all that different until you get down to much later in the bottom of the pile. I think it's going to be a preference for how you want to interpret things. The loadings are the x equals TP transpose. And so some people like to interpret those, whereas the weights are actually used to derive the basis, the scores, to keep the scores orthogonal. I think, honestly, it just depends on how you want to interpret things. But to start with, loadings are probably the easiest to look at.
Thanks. Okay, last call for last questions. I think finally answered everything about PLS here, Neal.
Yeah, I expect questions.
Yeah, feel free to send any questions you have about this into help desk, and we can get them if you think of something after we've signed off. Otherwise, I'd like to thank everybody, Neal and Lyle, and all our participants for joining us this morning.
Great. Thanks, everybody.
Just one last thing here. When I say variable importance, can I trace back to original variables and not latent variables?
Yeah, these are in
original variables.
Yeah, these are in original variables. These are the wavelengths down here.
Okay, we're 10 minutes past the hour, so I think we will wrap it up now. And thank you, everybody, for joining us this morning, today.
Thank you.
Thank you.
Bye.